So there is over 100 species of diving birds that exist, and they solve this challenge of moving in air and in water, which have very different densities in very different ways. To answer those biology questions, we have designed, prototyped, researched, and built a full robotic system that is able to go from the water through the transition out of the water and back to flight. And this is something that does not exist to this day at the bird scale. One of the interesting things is if you take a bird's wing and you put it underwater, the loads will be much higher because of the increased density. How birds cope with that is they fold their wings. And replicating this in robotics is challenging. Instead, we perform a similar function with flexibility. So we add significant bending flexibility in the wings, and therefore we can drive the wings at higher frequencies underwater, much closer to what we have in flight. How a flying robot can work underwater, we had to develop a motor drive system that would both provide the high frequencies for air, closer to 10 Hertz, and the low frequencies for water, closer to 1 Hertz. One of the interesting findings that we observed in our robots is that large wings, which are required for flight, are actually quite good underwater. And this plays in our favor because it means that we can have robots with relatively large wings, so pretty good in flight, that still operate well underwater.
Generally, the wings are made out of carbon structures and assembled with a membrane with a super hydrophobic coating that really repels the water. For transition, the water gets away from the wings very quickly.
Transitioning out of the water, everything has to be right and it needs to happen very quickly, which is the most energy-intense part of the whole cycle. Interestingly, we found that the angle of egress of transitioning out of the water is critical. And if the angle is within the vicinity of 70 degrees, we're able to get transition back to flight. If you want to do an underwater robot, you will get a housing that will float. And to get your robot to be neutrally buoyant, you will typically add weights in it, metal. If you do that, and you still intend for your system to get to flight, then it'll be simply too heavy to become a hybrid robot. So, to solve that, we individually waterproof electronic components. We get rid of the enclosure completely. Therefore, we have a system that's neutrally buoyant by itself. I care about developing the new tools for ocean research. And this is one of the promising technologies to be able to get the flexibility of flight and at the same time keep the capability of doing water studies by being in the water. My dream is that a scientist could take these robots in a car or even a backpack, could get to shore, take out the robot, throw it into flight, get to the destination, the GPS coordinate of interest, dive into the water, get a sample, get a measurement, fly back out and come back home to the scientist. If that happens, I'm happy.
The moments where you're really excited and where it's really worth spending all these hours is when you see the robot really getting out of the water. That's just incredible if you see that for the first time.